Hello NRF, Mr. Reed here. Just looking to do a little bit of a recap of some of the things that we had covered together before we went on the extended break, I guess you could say. So I hope everybody's doing well, and this is just to kind of, before we jump into anything, it's probably a little on the rusty side, so I'll go back to the beginning of the unit and we'll talk a bit about the real number system, and specifically rational numbers versus irrational numbers. So the idea really here is that number systems have been built up and made more complicated, I guess you could say, over a long period of time throughout history. So the natural number system is kind of just your idea of if you have objects in front of you, start counting them. So 1, 2, 3, 4, 5, etc. And that's basically your natural number system. Most of the things that have to do with counting work out great with the natural number system. And then all of a sudden, if you want to describe to somebody that there isn't anything there to count, it actually misses the idea or the concept of zero. So the whole number system is basically the natural number system, but it adds one more element or one more piece to it. And that is the number zero, which of course is fairly important in some sorts of statements. So for instance, in the natural number system, 2 plus 3 is equal to 5. Great. 5 minus 4 is equal to 1. Perfect. 7 minus 7 is equal to 0. But if you're only talking about natural numbers, the number 0 is not something that we consider or think about. So that's kind of a peculiar thing that happens. And so the introduction of this concept of 0 is really important. And that's all that really happens in the whole number system. Integers is obviously not as interesting, I guess you could say, from just a pure counting point of view. So if I am counting things, I usually am not concerned with counting -5 objects. That doesn't even really make much sense. So instead, we're considering things like, well, we have these other statements or expressions like 5 minus 4 is equal to 1. That's understandable, and we have all the values and needed to represent that expression or that equation, I guess you could say. So the idea with integers is, what if you come across something like 2 minus 5? Well, 2 minus 5 is not something that can be expressed with a whole number answer. But there are circumstances that we may come across where we want to be able to describe what 2 minus 5 is. So we need new numbers in order to do that. So in integers, we basically have the number line with all of the whole numbers on it, going from 0 to as large as you want to imagine, as long as you're skipping by whole numbers. The idea with integers is that there is a number line that goes in reverse from 0, starting at 0 and going -1, -2, -3, that we can identify, name, and talk about. We can show where they are on a number line, and they end up being the results to certain operations within this system. So like before, we said 2 minus 5 actually gives us a -3. And we can use these integers as well in the first part of expression. So if we would just want to say, what is -9 plus -3? Well, we can use them that way too and say, well, that's -12. So the idea of the integer system is that it incorporates both the whole numbers and then kind of this mirrored set of negative whole numbers, if you wish, that are also going to be included. Now, rational numbers get a lot more fancy, I guess you could say. So the idea of a rational number is that you can express a rational number as some integer divided by some other integer. So rational meaning ratio. So a ratio is 3 to 1, and you can think about it in terms of if you're doing some baking and you have I'm going to get exposed here. You have 3 cups of flour to 1 cup of sugar or something in some particular recipe. I'm sure that wouldn't make anything nice. But the idea is that it's a 3 to 1 ratio. It can also be expressed as a division. 3 divided by 1 is also the how big that ratio is. So any rational number can always be described as a ratio of two integers. So for instance, the number 1023 divided by -8, that is a ratio between 1023 and a -8, and therefore that value is what we call a rational number. So there's a lot of rational numbers, and rational numbers are very interesting because when we look at natural whole numbers and integers, we can kind of list them in order and know that we haven't skipped anything. The problem with, well, not problem, but one of the weird things that comes up with rational numbers is if I say, well, 1/2 is a rational number, and so is 1/3. And I say, oh, great. So 1/2 and 1/3, those, get smaller, 1/2 to 1/3. Have I missed anything in between them, though? And the answer is yes. You've actually missed an infinite number of values that are in between 1/2 and 1/3. Actually, if we put these on a common denominator to express them differently, we'd have 3/6. We'd have 2/6 for that first one, and then 3/6 for the second one, which, 2.5/6 would fit in between those two. Another way to say that then is 4/12, as well as 6/12, which means that there is in between those two a 5/12. But not only is there a 5/12, we could find a number that fits in between 2/6 and 5/12. 1/3 and 5/12. We could fit a number in between those, the new one that we found in the 1/3. We could fit another number in there. There's actually an infinite number of values that we could put into that position. So it's really hard to put these things on kind of like a really organized list of values. There's suddenly kind of an explosion where in between any two rational numbers, we can come up with an infinite list of rational numbers. So obviously we've made things a lot more complicated than just counting sheep that are walking by your window or something like that, which is what we could do with the natural number system. Now, the scary part is that we are also going to be discussing this concept of irrational numbers. So these are numbers that exist in the real number system that cannot be ever stated as a division or a ratio of two integers. Now, a lot of you are probably aware of some of these numbers and have seen them before. So for instance, the value of pi, so that's a Greek letter, and a lot of you know it as being about 3.14, is a special number that gives you a relationship between either the radius or diameter and the circumference of a circle. So you probably have used an equation before that allows you to determine either the circumference or the radius given the other one, and you're supposed to use this pi in order to make that calculation. Now pi is kind of famous for a number of different reasons, one of those being that it is an irrational number and therefore can't be expressed as the division of two integers. Some people will memorize massive amounts of digits of pi, and the reason why this is so impressive is because there is no calculation that they're doing in their head in order to come up with the next digit, because it's not just a straight division. It is instead just pure memory, and it's kind of a fluxing of their ability to memorize patterns or be able to store information in really interesting ways. So this pi, I cannot express it as a division of two numbers. Now there are divisions that give you values that are fairly close to pi and will approximate pi quite well, but nothing will give you exactly pi. So this is an irrational number. There are other irrational numbers that we will bump into. So if you have, for instance, 4, and we want to discuss the square root of 4, we've seen already this year that 4 is something that we call a perfect square. So there is a number 2 that when multiplied by itself gives us 4, the perfect square, which means that the square root of 4 is 2. So if we're just kind of labeling these as we go, this one's irrational, and this square root over here is definitely rational. It can be expressed as just 2, or if you want to, as 2 divided by 1. Now, if we go to, for instance, the square root of 9 and say, well, what does that become? We have that 3 times 3 is going to give us 9. So the square root of 9 is 3. It's another perfect square value that we started with, the 9. And so those are both rational numbers. Now, the interesting thing is, if we go and try to find what is the square root of 5, we're going to go on a pretty long search, I guess you could say, because if you break out your calculator and you go with the rule of you need to find a number that when multiplied by itself gives you exactly 5. So you're going to start putting values in. So 2 point something or other there. And so maybe go with 2.2. So 2.2 times 2.2, you find out what that is. No, it's not quite there, so you refine it, make it a little better. If you want the exact value of some number multiplied by itself that gives you 5, there is no rational number that gives exactly this answer. So that is very strange and very interesting. So what we had explored in class is the fact that it's not just root 5, it's all of the whole number values in between root 4 and root 9. So root 5 is an irrational number, root 6 is an irrational number, root 7, and root 8. Now there are values between 4 and 9 that do give rational square roots, but those will be things that are expressed instead in a fraction form where you get perfect squares in both the numerator and denominator. But if you don't have something that is a perfect square in both the numerator and denominator, which if you do not have a denominator written in, that's the same thing as saying that this denominator right here, so if I'm up, I'm up here right now, this denominator is like a 1. So is this denominator, it's like a 1. This denominator is like a 1 if I wanted to write those as fractions. So 4 is a perfect square in the numerator, 1 is a perfect square in the denominator, so we would have a perfect square in both those pieces. Gives you 2 over 1 or just 2 as the answer. Same thing with the 9, 9 over 1, perfect square up top, perfect square down bottom, numerator, denominator, good to go. The 5, that is not a perfect square up top. And even though it does have a perfect square down bottom with the 1, that's not good enough. So we are not going to have an answer for that particular value that is a rational number. So we need to be able to write these, and the radical symbol is going to be really important. That's this little piece right here. So the idea is that the kind of like that check mark symbol that's going to go over top of everything that's underneath of it there is going to tell us to look for the square root, or potentially, as we saw in class, the cube root or the 4th root or the 5th root. So as we make our way through those, we are going to be expressing this idea that all of the values in between perfect squares for the whole number options, not just any of the rational ones, those are all going to give you irrational answers. That's true for perfect cubes as well. So 8 is a perfect cube, and it's 2 times 2 times 2. The next perfect cube will be 3 times 3 times 3, which is 27. There are no perfect cubes that use whole numbers in between 2 and 3, because there's no whole number in between those two. So that means there's no value between 8 and 27 that will have a perfect cube that is a whole number as well. So if you do the cube root of 9 or 10 or 11 or 12 or all the numbers up to 26 inclusive, then we'll find that those are all irrational values as well. If you put any of these into your calculator and you are aware of how to take either the square root or the cube root of values, you can test any of the whole numbers in between the perfect ones that we know will not work out for us. So I'm just going to switch this for just a second. I had handed out a copy of this in class, but what it is it's a table that just shows you, and the one I handed out was the first 25. Up on the screen you can see the first 20. Perfect squares, perfect cubes, and perfect fourth powers. And again, there was the perfect fifth power on the sheet, but it's not really important, really. So the idea here is that we have numbers like 1, 4, 9, 16, 25, 36, etc. Those are your perfect squares, which means that any number not in that list, if you take the square root of it, irrational number. 1, 8, 27, 64, 125. Anything that's a part of that list, that's going to give you a rational number if you take a cube root of it. If it is in between those values, irrational number. Again, only considering whole numbers. You can do some funny things with fractions that do allow you to find values in between those, but nothing that has a denominator of 1, so we would be stuck. All right, so moving on to the fourth power one, 1, 16, 81, 256, same deal. If something falls on that list, it would have a perfect fourth root. If it doesn't, then and it gives you a rational answer. If it doesn't fall on that list and it's in between those numbers, then you are going to get an irrational number instead when performing a root there. So I'm just going to switch back and move along. So the idea is that we can identify when things are rational versus irrational by using kind of a chart, I guess we could say, because a lot of us probably don't feel super comfortable with having, for instance, the first 20 fourth powers memorized. Some of you may be really good at the list of squares. Some of you feel pretty comfortable with those. But if you don't, again, we can use some material just like that chart to help us out and identify them as we go through things. So if we are to answer the questions that I have listed off below me right now, determine whether the following are rational or irrational numbers, we can apply the same sort of thinking that we just went through. Basically, I'm going to pull up that chart here for a second. So I have that chart and I'm going to say, okay, the square root of 70, is it rational or irrational? Well, I don't really know my perfect squares off by heart, so I'm going to start picking my way through this list. So 1, 2, 3, 4, those are all my starting values, or maybe what I'm going to get as my answer. I'm going to take square roots. So I'm going to go to the x squared column. And we have 1, 4, 9, 16, 25, blah, blah, blah. I don't have to go through from the start. I'm looking for 70. So 70, not there. It's in between 64 and 81. So the idea is that I can guarantee, because 70 is a whole number, and 70 is not on my perfect square list, that means that the, yellow's not the greatest, that means that the square root of 70 is definitely going to be irrational. So it can never be expressed by using a ratio or a division, a fraction of two integers. So if we move over to the other example that's there, the fourth root of 81, we're going to do the same thing. We're just going to come over here into the x to the fourth column. And if I kind of skim my way down through that, again, 81 is the one that we're looking for. Oh, actually, it's there. So what that means is there is a perfect fourth power that gives me 81. If I want to read over to here, it's actually going to be the fourth power of 3. So because that's true, we can write that the fourth root of 81 has to be equal to 3, which 3, since it's 3 over 1, is definitely a rational number. And that's really all there is to the identification of it. I'm just going to use the chart or what I feel I know and allow us to come up with those statements, I guess. All right, so next up, what I want to talk about is if we have these irrational numbers, we want to be able to manipulate them, work with them, and one of the ways that we are going to be required to do that is by writing this radical symbol and being comfortable with different forms of the same statement. So what I have on your screen right now is this idea of entire, mixed, and simplified radicals. So over here, the square root of 80 is what we call an entire radical. So that is anything where the radical symbol is written and the only numerical piece to this is right underneath of the radical symbol. So you'll see the difference between these two and this one is that there is no coefficient, no multiplying number out front, and it is entirely underneath of the radical symbol. For a mixed radical, and so these are just terms that you're going to hear me use, and they're fairly well recognized. A mixed radical is one where you have parts of it that are underneath of the root, underneath of the radical, and there are parts that are outside as well, so in the coefficient position. So there is a 20 underneath the radical, there's a 2 that's out front. This is what we call a mixed radical. Over here, this is a simplified radical. A simplified radical is still a mixed radical, but there's something special about it. It actually is no longer possible to make the number that's inside of the radical any smaller than it currently is. So because of that, we call it simplified. Now, some of you may argue whether you think that this thing here or this thing here is actually the simplified version. So I was kind of comparing the entire versus the simplified radical. That's probably up for debate, but that's what we're going to call them. And the funny thing is, if you go and actually compare these three different radicals, they're actually the same number. And so that's why we need to be able to recognize that radicals can be written in different forms. Just like many of you probably feel comfortable with the idea of a third being the same thing as 2/6 or 3/9. Those are all the same value. Well, fractions have different forms. Radicals have different forms as well. So the next thing that I'd like to take a look at is how we're going to actually switch between howdy folks. So I was actually doing some work there and I hadn't switched back over to my iPad screen, so I'm going to splice this in and hopefully that's a little more helpful. And so the idea here is I have the third root of 40, and we have discussed in class that this can be expressed, and which is pretty straightforward for the first part. This could be expressed as the square root of 4 times 10, because 40 is just 4 times 10. I haven't done anything weird to that yet. But we did also show that that could be expressed as, the cube root of 4 times the cube root of 10, separated with a multiplication in between the two of them. We used some examples that simplified really nicely in class, so we showed that that was true. We also used some triangles to show that that made sense. So I think we took a triangle that was 1 unit by 1 unit, and so we said using Pythagorean theorem, we knew that the answer to that should be root 2. Then we doubled or scaled that triangle up by a factor of 2, and we said that 2 units and 2 units using Pythagorean theorem, 2 squared is 4 plus 2 squared is another 4, gave us 8. So the hypotenuse in that case would be the square root of 8. So therefore, 2 times root 2 is equal to root 8, which means that those two things are actually the same. And we showed that root 8 could be expressed as root 4 times 2, which is the same thing as root 4 times root 2, which at least in that case does give you 2 root 2. Same thing as what we had before. Great. So the idea of using that is going to mean that we can do that here as well. It actually does work out that way. However, what we're going to do is not get 4 and 10, because 4 and 10 are not helpful to us. If I bring back the chart there for a moment, if we take a look at the cube root, which is what we're currently covering, the cube root of 4, not listed on our chart. Cube root of 10, not listed on our chart. So in both of those cases, not going to be any good. No nice simplification going on there. So instead, we're going to search for values that we can pop in as factors of 40 that give me something nice in terms of a cube root. Now, we could search for these by having some number sense and kind of just feeling out what we think might work. And one of the ways we can make that work out a little easier is by writing all of the factors of 40. So if I just write these down, then I think we're done there. And the idea is I can search through that list for something I know is a perfect cube. And again, if I go back over to my chart, I have that in my cube column here, 8 exists. And 8 is one of the values that I came up with when doing my factoring. That's all well and good and works out well. But if you are up against something that's a little bit on the larger side and you really just don't want to find all of the factors, we could do a prime factorization of the number 40. And so the way that I mostly did it during class was to draw the 40 out, put a line next to it, and then just search for any prime factor of 40. So I know 2 goes into 40. Prime factor, great. It's going to leave me with 20. 2 goes into 20. So that leaves me with 10. 2 goes into 10. That leaves me with 5. 5 is a prime number. Whoa, don't want to do that. We want to highlight. All right, so 5 is a prime number. So 2, 2, 2, 5 is the prime factorization of 40. Now, since we're looking for cube roots, we are looking for perfect cubes in the factorization. So we might note that 2 occurs exactly 3 times. Even if it wasn't exactly 3, but it was actually 4 or 5 times, the fact that it occurs in a group of 3 means we can find a perfect cube that is a part of 40 as it has factors. So 2 and 2 and 2, perfect cube. That perfect cube is actually an 8. So I could say that 8 times 5 is a factorization of 40 that includes a perfect cube. And so I go back up to my cube root of 40 and I say, well, that's actually the same thing as the cube root of 8 times 5. And the reason we selected the 8 is because 8 is a perfect cube. So if I separate them like we said was possible, then we would see that the cube root of 8, again, I'm going to look over on my chart, say I don't know what it is. Oh, cube root of 8 is actually a 2. So what I'm going to say then is the cube root of 8 is 2, and then I'm left with the cube root of 5, and that is an irrational part. It can't be simplified anymore, and the factors of 5 are just 1 and 5, so there's no perfect cubes that are hidden in there that are left. So that is the simplified form of the cube root of 40. And we took a little while to get there. Once you get a little more used to the process of what it is that you're looking for, they're a little bit shorter than that, but we kind of just chatted our way through that. So moving on to the next one, if I want to go between simplified, which this is very similar to the answer that we just found. It's a little bit backwards, I guess. So we'll just totally get rid of what was there already and say 5 cube root 2. How do we move back into an entire radical form? This is actually quite a bit easier. So we're going to leave the part of the form that is already under the cube root. That's good the way that it is. This 5, though, can be written as the cube root of something. And so, again, I'm going to go back to that chart, or you can use your calculator, 5 times 5 times 5. Well, in this case, 5 times 5 times 5, if we look in the cube section, is 125. So what that means is, if we're working on this part right now, that 5 is the same thing as the cube root of 125. So the cube root of 125 and the cube root of 2 is kind of the backwards of what we were just looking at. We have these two expressions that can be written now, because they're multiplied together, as a single cube root by taking this piece and multiplying them together. So we would get the cube root of 250 is the entire radical form that goes along with the simplified radical, or it could have been a mixed one, but this one was simplified, of 5 cube root 2. All right, I'm going to move on. Oh, actually, that's good for now. That kind of catches us back up to where we were in this unit. So if you can find the time to do a little bit of the practice problems, I'll post them to the ones that we might have already done. You can go back through a few of them. If you have some time to do those, that'll get you caught back up, and I'll post another video a little bit later on, and hopefully we can move forward with this unit. And I hope that you're staying safe and that you feel like things are gonna be all right. If you want to chat or you want to send me a message about the math itself, please feel free. Take care.